Hello friends, previous chapter is a current electricity. In that chapter we study when electrons are flowing through a conducting material or conducting wire for unit time, then we say that some quantity of current is flowing through that conductor. When current is flowing through the conductor, then suppose this is a one conductor, AB is my conductor, and from that conductor I amount of current is flowing. When current is flowing through the conductor, then we observe the two effects. One is around the conductor magnetic field is produced. This is a one effect. And second one, when current is flowing through a conductor, then this conductor, the temperature of conductor increases, okay, or some quantity of heat is produced. Means the heat is developed. This is the one effect when current is flowing through conductor, and second effect is that magnetic field is produced around the conductor. That is a second effect. Okay. Today we see that only one effect, that is the magnetic field is produced around that conductor by a one chapter, and that chapter is a chapter number 10, magnetic field due to electric current. The reason behind the magnetic field is a flow of current through the conductor. So the name of chapter is a magnetic field due to electric current. This is an important chapter. If you clear all the concepts from this chapter, then it is very easy to understand the electromagnetic induction. Now, magnetic field due to the electric current. The magnetic field, this term is introduced by the scientist Oersted. Okay. Now, Oersted simple one experiment which you already studied in the 9th or 10th standard. This is the one conductor. Through this conductor, I amount of current is flowing. This is the first case. In second case, the current is flowing in opposite direction. And in the third case, no current is flowing through this conductor. Very close to this conductor, we have to place one magnetic needle. This is my magnetic needle, north and south poles of that magnetic needle. We have to place one magnetic needle here. Now, when current is flowing through this conductor, then what happens? The magnetic field around this conductor is produced. And when magnetic field is produced, and because of that magnetic field, what happens? This magnetic needle deflects, and this magnetic needle deflects in this way. Means the south pole goes in downward, north pole comes to the upward. Same thing it will be happens here. South pole goes to upward, north pole comes to the downward. And when there is no current is there, then there is no deflection in the magnetic needle. So easily we can conclude that when current is flowing through a conductor, around the conductor, magnetic field is produced. Okay? When current is flowing through a conductor, around the conductor, magnetic field is produced. So the first reason is how the magnetic field is produced. The answer is very simple. When electric current is flowing through the conductor, then magnetic field is produced. If I change the direction of electric current, then the deflection in magnetic needle changes. Means the magnetic field is produced. It will be changes. Means the magnetic field means what? The magnetic lines of forces. That magnetic lines of forces flowing in different directions. If I change the direction of current, means it is totally clear that whatever be the magnetic field is produced, that magnetic field is expressed by B. Okay, B is magnetic field, and that magnetic field is proportional to the amount of current flowing through the conductor. So if I change the quantity of current, then magnetic field it changes. Means current is of large quantity of current is flowing, then large quantity of magnetic field is produced. No current, no magnetic field. Less amount of current, less amount of magnetic field. If I change the direction of current, direction of magnetic field is also changes. Okay. So whatever the magnetic field is produced, that all the magnetic field is depends on the how much amount of current is flowing through the conductor. This is all about the Oersted conclusion. Okay, and what is the direction of current? It was given by the thumb rule. Okay, it is also called as the screw rule. It is very simple. We already studied in the test. Let a straight conductor carrying a current in upward direction. Okay, straight conductor carrying a current in upward direction. So we use this straight thumb indicates the direction of electric current. Then a curled fingers, the fingers, curled fingers, म्हणजे गुंडाळलेली बोटं. The curled finger shows the direction of magnetic field. This is the direction of magnetic field. This is the amount of current and this is the direction of magnetic field. If the straight conductor shows the direction of electric current, means now the current is flowing in downward direction, then again the curled finger shows the direction of magnetic field. This is my direction of magnetic field, and here the current is flowing in downward direction. So this is the direction of magnetic field, that is the B. Here current is in upward direction and the magnetic field, just see, it is in clockwise or anti-clockwise. You can easily get the idea. Current upward, then magnetic field is in anti-clockwise sense. If the current is in downward direction, then the magnetic field is 6 to 9 to 12 to 3, means it is in clockwise sense. So simply I will write here. This is about the direction of current and this is about the direction of magnetic field. The current is in upward direction, then the magnetic field is anti-clockwise. Okay, in some books it will be like this, anti-clockwise. If the current is in downward direction, then the magnetic field is in clockwise. Okay, but think in different way. If this is about the thumb rule, okay, just we go to one step forward. If the current is flowing in anti-clockwise sense, okay, this in this way the current is flowing. Let there is a one circular coil is there, okay, and the current is flowing in this way. Now, just I am writing here to your understanding. The current is flowing in anti-clockwise sense. Now tell me how the magnetic field is produced. Is there any another rule? No. There is the same thumb rule. Okay, when you recite the thumb rule, then we always recite in this way. If a straight thumb indicates the direction of electric current, then the curled finger shows the direction of magnetic field. But opposite thing is like this. If the curled finger shows direction of electric current, here the current is flowing. Okay, if the curled finger shows direction of electric current, then the straight thumb indicates direction of magnetic field. So the curled finger shows the current in this way, then a magnetic field is in upward direction. If the current flowing in clockwise sense, then the magnetic field is in downward direction. So this is my magnetic field, this is current, this is current, this is my magnetic field. So I am writing the same thing here. If the current is in anti-clockwise sense, then the magnetic field is in upward direction. If the current flowing is in clockwise sense, then the magnetic field is in downward direction. Okay, this is very important as per the thumb rule, or just we say as per the screw. So everyone note down this, the direction of current and the direction of magnetic field. This is very important to study the next answers. Okay, now we see when a magnetic field is produced, then what happens, when electric field is produced, then what happens. Suppose this is one conductor, through this conductor the current is flowing. What is meant by current? Current is simply, current is nothing but the flow of electrons per unit time. So if one electron is flowing, then a charge is 1.6 into 10 raised to minus 19 coulomb. Suppose there are n number of electrons are flowing, then the charge is given by Q Q equals to NE. But what is E here? E means very simple. This is a total charge equals to N means number of electrons and E means charge on one electron, that is a 1.6 into 10 raised to minus 19 coulomb. Okay. So current is given by, that is current equals to charge per unit time. Charge per unit time. So someone write it is a Q by T. Small q is, if I take the small q by T, or someone write in this way NE by T. We can use any one formula for the electric current. So note down this also. Electric current equals to Q by T or equals to NE by T. Okay. This is when the current is flowing through the conductor, then that current is given by I equals to Q by T or NE divided by T, where E is a charge on one electron which is given by 1.6, the charge on one electron is a 1.6 into 10 raised to minus 19. Okay, that one formula is important. So I am writing here I equals to Q by T. This is one required formula. Now come to this one. When this is a one positive charge is there, from the positive charge, electric lines of forces are emitted. These electric lines of forces are emitted from positive charge and ends at the negative charge. These electric lines of forces are experiences some force surrounding the medium, and that force is given by, that force is the electric force, because this force is produced because of this positively charged particle, means that electric force is given by, it is very simple, Q multiplied by E. What is that E? E is my electric intensity, okay, where E stands for the electric intensity. So this is a one more important formula that we have to note down this, that is a Q into E. This is my electric force. Is it clear? Okay, because we already studied in the last day. Now today we say that when current is flowing through a conductor, it produces a magnetic field, means some magnetic forces are developed. What is the direction of that magnetic force? The direction of magnetic force is similar with the direction of magnetic field. But if the two fields are present, one is the electric current is there, means electric field is there, and the magnetic field is produced. If the two fields are produced, then one force is developed. What is the direction of that force? All things we discuss here. Okay? And means we discuss first the magnetic force, then we discuss the Lorentz force, which is nothing but the magnetic force and electric force. That combination is nothing but the Lorentz force, that we also discuss here. Okay? So first of all, we see the first article of this chapter is the magnetic force. See very carefully. Okay, means the direction of magnetic force, magnetic induction, all things are discussed here. Okay, just we see that how you calculate the magnetic force comes to that part. Okay, it is very simple how to calculate the magnetic force or how to calculate the force. If magnetic field is there, okay, electric field is there, then how you calculate the force? It is very simple. Suppose one conductor is there, the electric force is there, magnetic field is there, means magnetic force is there, means on that conductor electric field and magnetic field, both the fields are present, then some force is developed on that conductor. That force that we have to calculate first. Okay, the direction of that force is simply, the direction of that force is given by a simple formula, that is the, suppose left hand rule. It is very simple. If the thumb indicates, means the thumb, first finger and middle finger, stretch the thumb, first finger and middle finger of the left hand in such a way that all are mutually perpendicular. See, in between thumb and first finger there is an angle of 90 degree, means both are perpendicular. Thumb and the middle finger, the angle between them is 90 degree, they are mutually perpendicular. And just see angle between these two, that is also a 90 degree, thumb and the middle finger, all are mutually perpendicular. Okay, now we have to discuss in this way. Suppose the middle finger indicates direction of electric current, the first finger indicates direction of magnetic field, then a stretched thumb indicates direction of force. Okay, F B I, FBI, like a Federal Bank of India. F force, B magnetic field, I current in this way. But how we can express that mathematically, that we have to see in this article, and it is very simple. If B is a magnetic field, just we know the symbols. B is my magnetic field, or the strength of magnetic field is also expressed by magnetic induction, and the V is the velocity. This is the velocity of what? This is the velocity of electrons. Okay, this is the velocity of electrons. Then the magnetic force is given by F. Magnetic force is given by E in bracket vector V cross vector B. But here the electron is moving, so charge on the electron is always a negative. So magnetic force is given by minus E in bracket vector V cross vector B. Okay, if E is the charge, suppose there is a charge on one electron, if there will be the number of electrons are there, then some students write NE for number of electrons into charge, V cross, this is for one electron, this is for n number of electrons. But remember that what is a Q? Q is nothing but charge, is nothing but n into E. So here I am writing minus Q in bracket V cross B. Okay, in magnitude. Okay, in general, for easy sake of convenience, we can write magnetic force equals to vector V cross vector B. This is my formula for the magnetic force. Fm, that is M magnetic, F force. Magnetic force equals to Q in bracket vector V cross vector B. So I am writing here magnetic force Q in bracket vector V cross vector B. This is a one more important formula. Now, if a conductor experiences both the forces, that is, if a conductor experiences electric force as well as the magnetic force, then what is the net force? Then it is very simple. Net force equals to electric force plus magnetic force. What is my electric force? Q into E. What is my magnetic force? Q in bracket V cross B. So the net force is how much? Q in bracket E plus vector V cross vector B. This is my net force, and this net force is F equals to Q in bracket E plus vector V cross vector B. This net force is nothing but this force is also called as, or this is the equation of Lorentz force. This is the most important to solve the numericals and to clear your concept. The Lorentz force is given by F equals to Q in bracket E plus vector V cross vector B. Remember, there is a cross product, and cross product between V and B is solved in this way: VB sin theta. Okay. So now we discuss when my magnetic force is a maximum, that we have to discuss first, or when the some observations related to this Lorentz force. Okay, that is very simple. So I am writing first the formula here, the Lorentz force. Lorentz force F equals to Q in bracket E plus V cross B. This is the formula for the Lorentz force. Now we discuss one by one some consequences of the Lorentz force. Now we see when this Lorentz force becomes a zero. Okay, that we have to see first. If the magnetic field is zero, then Lorentz force is zero. No, if QE is present, but we have to discuss only this part. If V cross B is written, then the magnitude of V cross B is given by VB into sin theta, because there is a vector product is there. Okay, if theta equals to 90 degree, theta equals to 0 degree, Then means what? If V and B are parallel to each other, then what happens? Then if both are parallel to each other, then what happens? VB into sine of 0 degree. But sine 0 is 0, so VB into 0. The answer becomes 0 and the magnetic force becomes a 0. If instead of 0 degree, if any other angle is there, suppose the angle is a 30 degree, 60 degree, 90 degree, then doesn't matter. We have exact values of sine theta. It is a 1 by 2. Then it becomes a VB by 2. Then a sine of 60 degree, it's a root 3 by 2. Sine of 90 degree, it's a 1. That is V into D. Means when a magnetic force is a maximum, when this theta is a 90 degree, then magnetic force is a maximum. When magnetic force is 0, when V and D are parallel to each other. When magnetic force is maximum, when V and D are perpendicular, because theta is 90 degree, means V and D are exactly perpendicular to each other. At that time, magnetic force is a maximum. Okay, this is all about the consequences of the Lorentz force. Okay, now the magnetic force is given by, I am writing here, magnetic force is given by Q V B sine of theta. Let me assume that the theta is 90 degree, then magnetic force is given by Q V B into sine of 90 degree. That is nothing but the Q V B. So one more form of magnetic force. If V and B are mutually perpendicular, then it is a Q V into B. Comes to this point. What is the V? What is V? V is velocity. How you calculate the velocity? Velocity is nothing but displacement upon time. Just that moving electrons covers a distance L per unit time. Okay, that is my velocity. So I am writing there equals to Q as it is L divided by T into T. But what is Q? Q is nothing but I into T. Are you getting this? Q equals to I into T. So I am using here I into T into L divided by T into T. So both are get cancelled. So magnetic force is given by I L B. If you want to use sin theta, obviously use, because we are taking the it is of 90. So this is the one more form. This is the magnetic force equals to ILB sin theta. For easy, it is a Bill sin theta. How? Bill? BIL is a Bill sin theta. ILB sin theta. So one more thing of the magnetic force, just I am writing here. It is a ILB sin of theta. Okay, this is a one more form. Now, if the magnetic force is given by ILB sin theta, just see, magnetic force is given by ILB sin theta. This is the magnetic force is given by ILB sin theta. And remember that L and B or V and D are mutually perpendicular, then it becomes a sin 91, that is a F equals to ILB. Then V is given by F upon RL. That is a magnetic force. Magnetic field is given by force upon current into length. What is the unit of force? Is Newton. Current is given by ampere and length is expressed in terms of meter. So the its SI unit is what? Newton per ampere meter. This is the one unit of magnetic induction. And we are already using the magnetic induction is given by Weber per meter square. Tesla is a one more unit. And with the same is Newton per ampere meter. Or simply the dimensions of this magnetic induction, we can easily calculate the dimensions. How you calculate the dimension? First of all, I am writing the force. Force means mass into acceleration. So meter per second square divided by current. Unit of current is ampere and length meter. So meter get cancelled and we are getting the dimensions. M raised to 1, then L raised to 0, T raised to minus 2, current raised to minus 1. These are the dimensions of magnetic field. M raised to 1, T raised to minus 2, and I raised to minus 1. These are the dimensions of the magnetic field. Okay, just see this part, and then we calculate the magnetic force for a straight conductor, magnetic force for the conductor which is of any shape or in a different way. For all that we are calculating this. Okay, see very carefully all the things and take a screenshot of last part. I will send you notes, write down that notes, and also send the questions. Okay, now we stop here for today.